not as fun as throwing orange papers into trash cans. Okay. So first question I have is, do you guys remember what the margin of error is from yesterday? It's like the distance from the center to the endpoints of the interval. Okay, and if we are estimating something, doesn't it make sense that you'd want that to be as small as possible because your estimate would be more precise? Okay, so there's two ways that you can decrease the width of your interval. The first one is kind of lame. You could decrease your confidence level. To have a smaller margin of error, you have to be willing to be less confident. I'm going to relate that back to Garfield. So Garfield's interval was really, really big, right? And we said that, you know, not thinking about meteorites or sudden complete freezings of the earth or something like that, we are pretty 100% confident that our weather is going to be between -40 and 200. But it's a really wide interval. If we wanted to say something like, we're pretty confident that our weather is going to be between 43 and 47 in the morning when we wake up, or 43 and 53, we're much less confident about that statement. So it's kind of like a common sense thing. But I also want you to think of it in terms of this, and this is where we're going today. I want you to think about 99.7% of the curve, 95% of the curve, 68% of the curve. Decreasing your confidence is decreasing the width of the interval. So think about those arrows being intervals. You see what I mean by the arrows? Okay. And it's not really that much of a spoiler because you drew the normal curve, I'm hoping, already on your paper, so you probably figured that out. Okay, and the other way is also kind of a common sense way, and it seems to be the thing that affects everything. Increase sample size. Larger samples have less variability. If you guys remember that from chapter 7. So that's a common sense reason. Larger samples have less variability, but we could be more confident in them. But it's also a math reason, because when we do our math, you guys remember how the sample size is in the denominator? So as you increase the denominator, the number gets smaller, and so it would decrease your margin of error. We're going to talk about that in the next statement, where I say, how do we calculate the margin of error? The first thing we're going to do is look at some chapter 2 stuff, your favorite, and I'm going to remind you that in the normal curve, these areas are 34%. And these are 13.5-ish. By the way, these aren't exactly 34 either, but apparently estimating like that rounding is very fine in stats. And what I want you to do is I want you to start visualizing your intervals. So like this little guy being a confidence interval, I want you to visualize him kind of living underneath the normal curve. Just like my poster back here. Do you have any idea how excited I was to find this poster last summer? I was like, oh man, I can use that in so many chapters. So this little guy would be a 68% interval because he spans 68%. What? Are you picturing me finding the poster? It's kind of embarrassing. Okay. And then this guy here, he's the most common one. That's what a 95% interval would look like compared to a 68% interval. So you're much more confident that your estimate would be in this range versus this range. What? What's wrong? Did I draw something wrong? No, not at all. No, it's fine. Okay. So, okay, now we need to talk about mechanics of this. And so I want to go back to yesterday where we talked about the pieces of the confidence interval. And do you guys remember me saying that this guy in the middle was the point estimate? And that either side was the margin of error? Really important. Okay. We need to start working on the mechanics of how that works mathematically, because I told you yesterday I didn't teach you the math, and I'm really not teaching you the math today either. A little bit of it. We're baby stepping into the math. But I need you to go grab your yellow sheet at this point and look on the front side, which we haven't used in a while, and find where it says confidence interval. You probably didn't even know that there was a confidence interval section on your yellow sheet. And on your yellow sheet, these pieces here are sort of broken down in a different way. So the point estimate is represented as statistic. That should make sense to you because that is something that's given to you from your sample. For chapter 8, it's going to be mostly proportions. So like 0.25% blue M&Ms in your sample. Plus or minus. Okay, and then it says in parentheses, critical value, which we need to define, times standard error of statistic, which we also need to define. Okay. I'm going to read this to you in what I think is probably as close to teenager language as I can get. This is saying, down the middle, plus or minus some number of standard deviations. Let me say that again. You have the middle point estimate, number in the middle, plus or minus some number of standard deviations. In this little interval here, this is one standard deviation. You see how I went out one spot on either side. And on this interval here, it went out two standard deviations. The standard deviation is going to be different for every problem. Okay, so when you're reading this, I want you to say, okay, number I get from my sample, plus or minus some number of jumps on either side. So how many jumps out? And the width of the jump is going to be standard deviation. Okay, and I need to teach you how to find all that stuff. If it helps you, you might want to put little marks here to show that there's like two jumps on either side. So this guy would be a critical value of 2. Just means you're going 2 out. This one means you're going 1 out. Okay, now the statistic in our chapter is going to be p hat most of the time. In a different chapter, it will not be p hat, but in this chapter, it will be p hat. And the critical value. Okay. Critical value is very important. So look back here at the poster. Man, what a good purchase. What? These are the critical values. So this is saying out 1 jump, out 2 jumps, out 3 jumps. Here's the 1 jump, that was 68%. Out 2 jumps, which is 95%. What are these guys called? These, right, those are z-scores. Okay, however, because we have the plus or minus in front, the critical value is always going to be positive because it's just a number of jumps. And you're already taking into account the negative because you have plus or minus there. So when you're talking about just the positive, this is called Z star. Z star is nothing other than the absolute value of Z. You just make it positive because you're just going out that many spots on either side. Okay. For proportions, I'm hoping this was not going to be that surprising to you, but the margin of error, and this is what I use to abbreviate margin of error because I'm lazy and I don't know that there's any specific way to do it. Okay, the critical value would be Z star. It is for both. That just means how many jumps I'm going out on either side times standard deviation. Do you guys remember? It's P times 1 minus P over N. That's from chapter 7. Do you guys have a recollection of that from chapter 7? If you don't, it's okay. The one for means is Z star, so number of jumps, and the standard deviations are standard deviation over the square root of the sample size. Okay, now can you guys find your yellow sheet? We're going to write some things on there, so this is very important. As soon as you get your formulas. The first thing I want you to write is a little bit of vocab and sort of a note for where to draw your eyes when you're taking the test. So during chapter 8, I want you to focus on this line here. I'm going to allow you to say that the statistic is the point estimate and that those two pieces of the like multiplied after the plus or minus, I'm going to allow you to label that as the margin of error. And then for this chapter, it's not always Z star, by the way, but for this chapter, the critical value will be Z star, and you can label him up there. There's actually more curves than just the normal one. Will we need them for chapter 8? No, they will just be these. Okay, now flip to the other side. And when you're ready, there's a little bit we need to talk about there. I need you to add those two things. And we need to talk about what is happening here. Okay. What? This is chapter 7. This is chapter 8. This is what we used on our, like our Christmas test. What is the difference between this formula and that formula? Yeah, okay. These are perfect mathematical models that we use, sampling distributions, all possible samples made into a beautiful sampling distribution model of perfect normal curveness. These are saying, now I'm in real life, I don't know what the population stuff is. Why would I do statistics if I knew that? My best number to use is the one from the statistic, from the sample. These two are the same thing, it's just that I don't have access to the population stuff anymore, because that's real life, you're never gonna have that. So my best guess is to use the number I got from my sample. Okay, now, can you guys, notice that there's a star, there's an asterisk next to standard error of the sample statistic? You guys see the asterisk? Okay, go to the bottom of the page. And we're just gonna read this together one time real quick. Standard deviation is a measure of variability from the theoretical population. Standard error is the estimate of the standard deviation. If the standard deviation of the statistic is assumed to be known, then the standard deviation should be used instead of the standard error. Okay, what the heck did that say? That's saying if you have P, you should use it. If you don't have P, you have to use P hat. Let me say that again. If you have P, you should use it. P is the best possible scenario. P is theoretically perfect. But if you don't have that, default over here to P hat. So best case scenario, also pretty good. Use if you can. If you can't, use this. Okay. All right. So we're done with that. You can put that aside. The next thing I need to teach you guys how to do is Z star. So I need you to grab your calculators for that. Okay. We're going to find Z star in the calculator, except the thing is, Z star is constant. So once you find it, you can just use it. The one for 95%, I promise you, you will memorize and you will never have to do this again. The other ones, you might not memorize. In the homework tonight, you're going to find some of them. We're going to find some of them in our example. So anyway, okay. I don't know if you remember, but from chapter 2, you can find Z by doing inverse norm. And what you want to do is you want to find the Z for this spot or this spot. Okay, and so I made you a formula because children love formulas. What you do is you do 1 minus the confidence level. I'm going to do 95 in here because that's the most common one, but you should put whatever the percent confidence is that you have divided by 2. And then you're using the standard normal to find Z. So your mean and standard deviation is 0 and 1. There are so many children who ask me during the test how to find Z star. And I'm just giving you a heads up now that I will not be answering that question during the test, because that shows me that you haven't even tried to pick up a calculator or do it one time before the test. So I highly suggest you practice this, but if you have your own calculator, you can kind of cheat because you could leave this in there and then just change the confidence level every time because it'll just leave it in there. Okay, so do you guys remember where to go for inverse norm? Second vars. You guys remember? Second vars. Okay. Area is parentheses 1 minus 0.95 divided by 2. Make sure that the parentheses are just around the top. And you want it to be left. If you don't have those options, it's already left. Okay. And this is annoying because we talk about it being 2 standard deviations away when it's 95%, but it's not perfect. Okay, so what you're going to do is write, oh goodness, I hit it a bunch of times. Absolute value of negative 1.96 equals 1.96. So remember, Z star is an absolute value. You've already covered yourself with the plus or minus. Okay, so I highly suggest you just leave this bit in your calculator, and in every problem that you do, that'll still be there. Just go change this decimal to whatever that particular problem says. If it says 90%, change it to 90. If it says 99%, change it to 99, but just leave this in there. That is my suggestion. Okay. I don't know why I left so much room here. If you're somebody who can cram your notes, I feel like you can cram this lesson a lot. I used a lot of space. I don't know why. Fine. Totally great. Okay. This is the last little bit, and then we're going to do the example, which is the random sample of 25 students required them to state their GPA out loud, which I think is hilarious. But anyway, okay. So what margin of error does and does not count for? Why do we have margin of error? Why is that a thing? The reason we have it is because of sampling variability, because samples change from sample to sample, right? Do you guys remember my battleship picture? And it was like beam, 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 beam. Margin of error is just sort of allowing your estimate to account for that. That's the only thing. So variability due to random sampling. Yes, that is the only thing margin of error does. It accounts for variability due to random sampling. You don't know if you got a weird sample, so you're being careful with your estimate. Okay, what does it not account for? Bias in the design of your study. If your study sucks and you have bad questions or a bad method, it's not going to fix that for you. What types of things should you be on the lookout for? What do I mean by that? Voluntary response. You can't say, oh, well, it's fine because I'm not really estimating a real number. I'm including a margin of error, but it's a voluntary response sample. It doesn't fix that for you. Under coverage. Do you remember what these things are? This means like a whole part of the population is not reachable. Non-response. That means that someone was chosen in my random sample, but they did not respond, chose not to respond, or there was something wrong with their response that couldn't be used. I had this happen to me over break. So my son is applying for the CHP. I don't know if you guys know how invasive the application process is for the CHP, but they sent postcards to all of our neighbors to ask if my son is a good person. And my neighbor is 91. Can I flip this over? You guys can do your arts and crafts while I tell you my story. Everybody got this situation? Okay. Okay, so she's 91. First of all, I'm taking a nap because it's the middle of the break and that's what I do. That's my normal phase is napping. I'm taking a nap and I see the ring camera go off and I'm like, yeah, and I wake up and I was like, oh no, it's going off again. And it's our 91-year-old neighbor. My first thought is he needs some kind of assistance or something because she's 91. I go out there and she's like, I got this postcard. This is my voice for her, by the way. I got this postcard about this, about the EXP. And I was like, oh my God. And by the way, they went to his work, like literally, CNP officer went to his work to ask about it. They did an in-home interview, just in case any of you are interested in pursuing that. It is serious. But so 91-year-old neighbor, she's like, I don't know him because she's 91, she doesn't come out. And she's like, I'd like to give anyone in your family a good recommendation though, because you guys are all really nice. Good neighbors, right? Okay. So she's like, will you do it for me? It's got a QR code on there. Like, I don't even know how she would have, but whatever. It's fine. Just picturing the old lady with a postcard with a QR code on it. So I was like, sure, I'll do it for you. So I do it. I'm filling it out for her. And then the comment box I put up. He seems like a nice boy from a nice family, because that's kind of what she said on the doorstep, right? And the whole point of the story is I'm getting to the part where it asks for an email. She's 91, she doesn't have an email. So I'm like, try to leave it blank, it won't let me. And then I'm like, they're like, okay, I don't know what to do. So I do ChatGPT because that's my favorite. And I'm like, what do you put if someone doesn't have an email in their required survey? And ChatGPT goes off about how you should never require someone's email in a survey. And if you do it, like completely invalidates the response. And then it said, though, a lot of people use like no email at none.com. That's what I did. I ended up doing no email at none.com. Which might have completely invalidated my response, which means that that particular postcard might have been non-response. Because these are the things I think about, right? So by the way, he has to get hooked up to a polygraph machine on the 19th and asked about everything in his background check.
What are they doing about it?
Well, I mean, it just depends. No one wants to. No, I get it. I get it. But he told me this weekend that in the academy, if he makes it, just like let everyone in the room keep everything crossed and he makes it if he really wants to do it with somebody. I feel like, and I realize I'm recording this right now, he's gonna get to his first really bad traffic accident and he's gonna be like, I can't do this, and like the whole thing will be moved. But whatever. So he told me he has to get tased, pepper spray, and tear gas in the academy. Yeah, it's required. They want them to have empathy for the tools that they use to like understand the strength of it. It makes sense. I know. Okay, but if you watch the show Chips from the 1970s, they do a lot of things that you would not expect. Highway patrol. Right? I did not know all of this stuff. I've just blown away. All right, you guys ready? You guys ready? Okay. Yep, we need to go quick though, because I have wasted all your time with my story. I mean, none of this is challenging really, but it takes a minute to write down.
And it goes all the way to E. Yeah. 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 Lexi's chilling. Okay. All right. A random sample of 25 students required them to state their GPA out loud. Hilarious. A 90% confidence interval of 0.4 to 0.72 was calculated for the proportion of students at the school with GPAs greater than 3. So 40% to 72% had GPAs over 3. Calculate the point estimate and margin of error. Okay, that's easy. Zero point 0.72. Everybody good with my point estimate? Just found the middle. Okay. And then margin of error is going to be the distance, but actually this one's easier, huh? 0.56 minus 0.40 is 0.16. So margin of error is 0.16. By the way, that is exactly the very first, not the same problem, but that is the very first directions of the multiple choice part of the test. That's the very first question. You have a low and a high, find point estimate and margin of error. Draw a little picture, find the middle, subtract. Easy. 1 point, guaranteed. Okay, explain what would happen to the width of the interval if the confidence level increased to 99%. Okay, so it was 90% and it went up to 99%. What would happen to the width of it? So let's just label our stuff here. This is 90. And it would go to 99, which would be much wider, right? And I want you to think about that in terms of like covering the area under the curve. So like 90% of the area under the curve, 99% of the area under the curve. Okay. C. Calculate the critical value Z star for a 90% confidence level, then a 90%, 99% level. So these two previous ones in A and B. Remember what the critical value Z star is, how many standard deviations out on either side. So 90 should be smaller Z star equals inverse norm 1 minus 0.90 over 2, 0, 1. This should still be in your calculator, and all you need to do is go change that 9.5 to a 9.0. Okay, now, if you're on the memorizing track, for some reason, this one, everyone says 1.96, but for this one, everyone says 1.645. Like, if you just look it up, it's gonna say 1.645. I don't know why they round this one to 2 decimals and this one to 3 decimals. I guess that's because it's a 9, but anyway, okay, so absolute value of negative 1.645 equals 1.645. I have two of them memorized, I would say, the 95% and the 90%. Yes, honey? Nope. And as a matter of fact, you don't need to write any of this on the test. You just need to say what the number is. You don't need to show any of this work. You just need to say Z star equals. But we're just learning right now. And the reason is because it's constant. So once you find it, you don't ever need to find it again. Unless you forget what it is, you should know how to find it. But none of the stuff I'm writing now is necessary. And you don't ever have to write the absolute value bit either. I'm just doing it because it's notes. I really want these to make sense to you though. You guys imagine that 90%, that this is 68 and this is 95, that 90 would be like 1.6 on either side. And that 99 would be like 2.6 on either side. Can you see what I mean? Like 2.6 would be just a little bit less than the 99.7. Just saying, just want that to like actually make sense to you. Okay, we have two more things and then we're done. Now, this is actually a chapter 7 question. You guys remember what happens when you increase sample size? You decrease variability. And variability is the width of the interval. So the width will decrease for two reasons. First, it's because the number in the bottom, the denominator will go up, so that will get smaller. But also because if your sample size is bigger, then you can trust it more, right? So there's a little bit of a thing here though that I want to remind you. So I don't even know how to say that. Is there a word for less wide? Skinnier? I don't know. It would be less wide. Okay, however, there's a very special property in this particular problem that I brought up on purpose that we were working on in chapter 7. What was the original sample size in this problem in your example? 25. So I'm going from 25 to 100. 4 times bigger. What is the square root of 4? 2. So that means it would be half as wide because the 2 is in the denominator. Do you remember how I did that on the board back there? I was like square root of 4 Anyway, okay, so we're just gonna write ourselves a little note. Okay, last thing. And this one is so simple. I'm hoping that it was just screaming out to you as you were reading this problem. Or saying it out loud to yourself. There's your hint. Are you sneaking in chapter 4 with you into chapter 8? What? Me?
No.
Like I'm putting kale in your smoothie. You don't even know. It'll taste like fruit. Anyone have kale snuck into their smoothie before? You don't even know it's your vegetable. We were just talking about this yesterday. Mr. Kevin is trying to convince me that I would eat kale if it was cooked with bacon. So I still don't know. I don't know. I don't know that there's enough cover up there. Okay, what is the screaming source of bias in this particular example? Think back to your chapter 4. What? Okay, what is that called?
Being a liar.
Desire to please bias. Desire to please bias. I just added that note. It didn't ask me for that, but just remembering how we overestimate, underestimate. This one's probably overestimated because people would say their GPA is higher than it actually is. We're done. Other than my joke, I'm trying to remember if it's actually funny. Oh, do you guys know the More Cowbell skit from Saturday Night Live?
What?
More cowbell. No. I know you're all very young. Um. It says, I never construct confidence intervals, but when I do, I make them wide as possible. If you picture his voice in the skit, it's really funny. And he says, I got a prescription and no, I've got a fever and the only prescription is more cowbell. It's funny. I promise you. It's funny. Maybe if you're an old person, it's funny. No, it's a good one. Callie. Callie.